Have you ever wondered how some chemical reactions happen in a split second, while others seem to take forever? Well, a lot of the time, the secret ingredient is something called a catalyst. In this explainer, we're going to break down exactly how they work, focusing on the stuff you absolutely need to know for your syllabus. So here's the game plan. We'll kick things off with a solid definition. Then we'll jump into the two main types, heterogeneous and homogeneous. We'll use the specific examples from your course, and then we'll see how it all connects to a huge real-world issue, acid rain. Okay, first things first. Before we go any further, let's get a really clear idea of what we're talking about. What exactly is a catalyst? So what it all boils down to is this. A catalyst is something that speeds up a reaction, but, and this is the key part, it doesn't get used up in the process. You can think of it like a shortcut on a hiking trail. It provides an easier, lower energy path for the reactants to become products. And once the reaction's over, the catalyst is left totally unchanged, ready to do it all over again. Right, let's get into our first major category, heterogeneous catalysis. The word to focus on here is hetero, which just means different. And that's your clue. This is when the catalyst is in a different physical state or a different phase from the reactants. The textbook example for this is the Haber Process. It's a massively important industrial reaction that makes ammonia for fertilizers, the stuff that helps grow a huge amount of the world's food. So in this process, we have nitrogen and hydrogen, which are both gases, reacting on the surface of a solid piece of iron. You've got gases and a solid, different phases. That makes it a perfect example of heterogeneous catalysis. And for your syllabus, you need to know how this happens in 3 steps. First up is adsorption, which is really just a fancy way of saying the gas molecules literally stick to the surface of the solid iron. Then, in step 2, this connection to the iron actually weakens the super strong bonds inside the nitrogen and hydrogen molecules. This makes it way easier for them to break apart and react with each other. And finally, once the new ammonia molecule is formed, it detaches from the surface. That's called desorption, and it leaves the catalyst surface totally free for the next batch of reactants. Okay, time for our second type, homogeneous catalysis. Now, if hetero meant different, you can probably guess that homo means same. And that's exactly right. This is where the catalyst and the reactants are all mixed together in the very same phase, like everything's dissolved in water or it's all just a big mix of gases. So, here's the big difference in a nutshell. With heterogeneous, the action happens on the surface of the catalyst. But with homogeneous, everything's swimming around in the same pot. The catalyst actually jumps into the reaction, gets changed into something else for a moment, we call that an intermediate, before it gets regenerated or kind of reborn at the very end. Let's look at the first example you need to know. The reaction between these two ions, iodide and peroxosulfate, is super slow on its own. I mean, you'd be waiting forever. But if you add just a little bit of iron 2 ions into that solution, bam, the reaction suddenly just takes off. Now, pay close attention to this first step, because this is where it gets interesting. Our catalyst, the Fe2+ ion, actually gets used up. It reacts with one of the reactants and gets oxidized, turning into an intermediate form, the Fe3+ ion. For a moment, it looks like our catalyst is gone. And here's where the magic happens. In step 2, that intermediate we just made, the Fe3+, reacts with the other reactant. And in doing so, it not only makes our final product, but, and this is the whole point, it regenerates our original Fe2+ catalyst. It's back to how it started, ready to kick off the whole cycle again. Okay, for our second example, we're moving from a beaker of solution to the air all around us. We're looking at a reaction between gases, where nitrogen dioxide acts as the catalyst. And this one has some pretty serious consequences for the environment. And look, you're going to see the exact same 2-step pattern. In the first step, our catalyst, nitrogen dioxide, reacts with a pollutant, sulfur dioxide. The catalyst gets consumed and changes into a new intermediate. This time, it's nitrogen monoxide. Then, in step 2, that intermediate, the nitrogen monoxide, reacts with oxygen from the air. This reforms our original nitrogen dioxide catalyst, which is now free to go find another sulfur dioxide molecule and keep this whole damaging cycle going. Now, this is the really cool part. If you take those 2 reaction steps and add them together, just like you would in math class, you can cancel out anything that appears on both sides. And watch what happens. The catalyst, NO2, and the intermediate, NO, they both just disappear. And what we're left with is the simple overall reaction.
This is the ultimate proof that a catalyst is part of the journey, but it's not part of the final destination.
So, why do we care so much about this particular catalytic cycle with nitrogen dioxide? Well, it's because it's directly responsible for a major environmental problem: acid rain. You see, that sulfur trioxide that's produced in the reaction doesn't just hang around. It mixes with tiny water droplets up in the clouds and forms sulfuric acid. And sulfuric acid is the main nasty ingredient in acid rain, which can damage forests, lakes, and even buildings. So, from creating fertilizer that feeds the world to creating acid rain that harms it, catalysis is this incredibly powerful force. It's not just something in a textbook, it's happening in the catalytic converter in your car to clean up exhaust fumes, and it's happening with enzymes in your own body to digest your lunch. So the real question is, now that you know what to look for, where else are you going to spot these hidden chemical helpers and hazards at work all around you?